Hello students. In the previous lecture we started looking at the RISC-V ISA and we picked arithmetic instructions to understand some of the design principles of the RISC-V, and we looked at the types of operands, namely the register operands and immediate operands. Today we are going to look at the third type of operands, and before that a quick a discussion about various types of operands that RISC-V supports. Right now, why do we have so many different types? Let's try to answer that question. In an instruction, we have the operation and operands, and operands are the data on which we want to perform that specific operation on, right? And in there can be source operands and destination operands. Now, the question would be, from where will we get this data from? Will the data be available in the registers, or will the data be available within the instruction itself, or will the data be available somewhere else? Right? Accordingly, we have different types of operands. The very common operand would be the register operand, right? RISC type architectures are heavily built on this. The value or the data that we want to operate on will be available in a register, and the register number, or you can say it as the register's address, is available or encoded into the instruction when we are converting from the assembly code to the machine code, right? So that the hardware, when it looks at that machine code, will understand where to get the data from. So we saw a few of the arithmetic instructions with register operands. Following that, we also looked at a possible case where we don't need a register operand, but rather the value we want to operate on or use in that operation is encoded in the instruction itself. Right? That's why it's called immediate. We don't need to go to any other place. We can directly take it from the instruction itself. Now, what about the data that is not currently available in the registers? What to do with them? Because the number of registers are very small, 32 to be very precise, and x0 is always 0. Effectively, we have only 31 registers, and let's say you want to work with an array of 100 elements. Now, at any given moment, only 31 of them are available in the registers. So in that case, what to do? So to support those kind of scenarios, RISC-V provides us with the third type of operands called memory operands. In these memory operands, what basically happens is the address of this operand is available in a register, and just like the register operand, this particular register's number or address is encoded into the instruction. Now, what does the hardware do once it identifies that it's a memory operand? How it identifies, we are going to look at it in the next module, when we are actually looking at execution of each instruction a little more in detail. But at this moment, let's assume that the hardware identifies that it's a memory operand. At that point of time, it goes to the register whose address is given in the instruction, picks the value, sends it to the memory, and the memory will respond with the data, and that's when we will be able to operate on. So let's look at the memory operands a little more closely. Primarily, the main memory is used for all sorts of composite data, the arrays, structures, dynamic data like heaps and stack, etc. And it's anybody's knowledge that the size of this data is typically much higher than the registers that are available. So many times we need to access the memory. Now to perform the arithmetic operations on such data which is not readily available in the registers, the very first thing we do is to get them into the registers and then use that register for as part of any arithmetic instruction. So to get the data from the memory and place it in a register, what we have are some load instructions. What does loading mean? We load the data from the memory into the registers. Now when we are done using the data, or we want to store the data that has been result of an operation, we use what's called store instructions. Now store instructions, what they do, they take the value from some register and write it to a memory location, right? So these load and store instructions together are called as data transfer instructions. The memory of RISC-V is byte addressable, and little endian assignment or alignment is followed. And if we look at the word alignment aspect, RISC-V does not require words to be aligned in the memory. But word alignment is one of the primary requirements for many ISS that we currently see. Couple of other ISAs that do not require word alignment are the popular x86 ISAs, and one example of ISA which requires word alignment is MIPS. So x86 is a CISC type ISA, and MIPS, as I mentioned in one class prior to this, is belonging to RISC ISA. Now, important point that I would like to all of you to note is that in RISC-V, only the data memory, means the place where all the data is stored, is relaxed of this word alignment. But when we look at the instructions, they are always word aligned. Okay, keep this in mind, and you will realize this aspect when you are using the data transfer instructions in Venus also. Venus exactly is built the way we expect a hardware that is based on RISC-V ISA is supposed to work. Couple of examples where memory operands are required, like I mentioned, the load instructions and store instructions. To understand them, let's look at a simple C code. So here what we want to do is we want to add a value h to the element a of 10 and write it to an element a of 12. Now let's assume that the array A is an array of double words, and in RISC-V a word is of 32 bits. It means this is an array of elements where each element is of 64-bit size. Let's also assume that the value of h is available in register x21, and the starting address of A, which we can also call as the base address of A, is available in register x22. Now to write or convert this line of C code into the RISC-V code, we first need to calculate what's called as offset, or where an element of array is available when we have only the starting address. So we can call that as an we can try to interpret that by using a generic index I, a of I, for example. And if we have a of zeros address, a of I can be obtained by adding this address of a of 0 with a value 8 times this index I. Now why is it 8? Because A is an array of double words. 64-bit is 8 bytes, and RISC-V, because it's byte addressable, it means that A of 0 and A of A of 1, if you look at the address, they are 8 spaces apart. Now a quick example here. If A of 0 is, if we consider it to be stored at location 0, then A of 1 is available after 8 locations. So the offset would be plus 8. If you want, let's say, to get the value A of 5 and we have the starting address A of 0, then we need to add 40 to the base address to get the location of A of 5. So with this understanding, when we want to if you want to write the RISC-V code for this single line of C code, it would look something like this. First, we use a load instruction. LD is the mnemonic for that, and the way we would read it is LD x9, 80 x22. Now what does this do? The base address of array A, which is available in x22, is added with an offset of 80, right? This resultant will be sent to the memory because that is the location of A of 10, right? Whatever value is there in that location will be returned to the register x9. Following that, we have the simple arithmetic instruction add, wherein the destination register is x9, one source register is x21 in which the value of h is stored, and the other source is x9 itself. So we are performing h plus A of 10 here. Following that, the resultant of this addition should be written to a location A of 12. Now how do we get A of 12 when we have the location of A of 0? So we would add 96 to the base address, which is in x22. That's when we'll get the location of A of 12, and then we using this we write a store double word instruction. SD is mnemonic for it. Store double word the value which is in x9 into a location given by x22 plus 96. So this way we are able to perform A12 equals to h plus A10, A of 10, right? So we need these data transfer instructions to get the data from memory, work on them, and whenever we are done, write back something else to the memory. So using a store instruction. If the array A was not made up of double words but rather with words, then we have load word and store word instructions, and add W also, right? It will add two data items which are of size 32 bits. So accordingly the offset will also change. Now A0 and A10 are not 80 spaces apart, but rather they are 40 spaces apart. So the offset will be 40 here, and for A12 it would be 48. Rest all would be still same. So we are getting the value of A10 into register x9 here using the load word instruction. Then we are adding the value of h to the value of A of 10, and the resultant which is in x9 will be returned to location A of 12. Not only the load double word and load word, RISC-V also gives us many other sizes to work with. We can work with data which is of just of the size of byte using load byte and store byte. If it is word, load word, store word. If it is half word, which is 16-bit, then we would use load half word LH and store half word SH. And like we already seen, double word would require LD and SD. So in general, the registers that are holding the base address of a memory location, it's called base register or index register, and the value that we add to this base registers at value is called offset. So we can say that this is base plus index type of addressing. Okay, we are going to talk about the addressing mode supported by RISC-V probably at the fag end of this module. But at this moment, you can uh, uh, you can see that we the data we want to operate on will be either in the register or within the instruction itself, or it can be part of the memory. To get it to the CPU, we need a load instruction, and to write back the result, we need a store instruction. So which would be the memory operands, right? And typically, based on the sizes we would have defined when we are writing the code, the compiler will calculate the offsets and write the assembly code appropriately. Okay. Now, if we have a quick doubt on why we would go to the memory instead of using the registers, uh, because the registers are very fast, we have already touched upon this point. Though registers are very fast, their numbers are very less, right? So we can't have all the data readily available in the registers. That's why we need the data transfer instructions. Operating on data which is residing in the memory requires the loads and stores. It also means that even though we wanted to execute one line of code, a of 12 equals to h plus a of 10, we ended up writing 3 lines of assembly code, and 2 of them were the data transfer instructions, one to get the value a of 10 and other is to write the result into a of 12. So even though we wanted to perform only one operation, we ended up executing 3 instructions. This is typical of any load store architecture. Now, because the registers are fewer in number, the compiler must carefully use the registers, otherwise it will end up inserting or introducing lot of loads and stores into the assembly code. So a compiler, before it finally generates the assembly code, will analyze the program so that it will remove any unnecessary load and store instructions. For example, we have declared a variable but we did not use it. So the compiler in some of the optimization levels, uh, by the way, which was one question that I gave you in lab assignment 0, is to work with different optimization levels of the compiler. By default, if you just do GCC, right, GCC, and you give the source code, it would generate the optimized version with level 3. So instead, you can have different levels which you can give at the command prompt as O0, O1, O2, or O3, right? You can just play around and see how much time each of those code takes to execute for the same program, by the way. So the compiler at when the optimization flag is set to high, it will analyze the entire program to do some additional optimizations like this, right? We are going to look at some other optimizations also as we go. So whenever we want to write the data from which is residing currently in a register to the memory, and after some time we want to get it back from the memory to the register, so on and so forth, this is called register spilling. So register spilling effectively means that we are doing a lot of data transfer between the memory and registers, which is not good. That's the reason usage of registers in an optimized fashion is very important, and that's where the compiler plays a crucial role. Coming to the encoding that the load instructions follow, it is the immediate format or I format. So earlier we saw the I format from the immediate arithmetic instructions perspective, now let's try to visualize the same when we are looking at a load instruction, right? So RS1 would represent the base address register's number, and the immediate value that we give as part of the instruction will now be interpreted as an offset, which will be added to the base address. And this address will be sent to the memory via the MAR, memory address register, and the value that is replied, that the value we get as a reply from the memory will be placed in the destination register. So a quick point, the immediate value is always a 2's complement value with sign extension. If you look at the instruction encoding followed for the store instructions, it's a new format called S format. It would look something like this. We have again 6 fields in it, opcode, immediate 4 to 0, 5 bits, followed by function 3, followed by RS1, followed by RS2, and 7 bits of immediate field. So the RS1, again similar to the load instruction, it acts as the base address register's number. RS2 is the source operand. It means the value in RS2 will be written to the address given by RS1 plus the immediate value. So the immediate value is obtained by concatenating these two sequence, then we'll get 12 bits of immediate value. Now if a question arises why we are splitting the immediate like this instead of placing the immediate field as a 12 bit continuous 12 bits of continuous in a single location. So again it's basically to preserve the positions of RS1 and RS2. In the typical arithmetic instructions, the R format, if you see, RS1 is always here and RS2 is always here, right? To follow again the regularity aspect comes into the picture. That's the reason the encoding is decided such a way. So S format you can remember easily for store instructions. So thus far what we have seen are few R format instructions, the add and subtract, right? They have 6 fields, opcode followed by RD, function 3, RS1, RS2 and function 7, right? And when it comes to the I format, we have few immediate arithmetic instructions, and we have shift instructions with slightly different variant of the I format, but they are still can be grouped as I format instructions. And along with that we have the load instructions, wherein we have the opcode RD followed by function 3, RS1 and 12 bits of immediate field. The store instructions have their own unique encoding again. So we have the opcode, 4 bits of immediate value here, followed by function 3, RS1, RS2 and the remaining bits here. Sorry, 5 bits of immediate field here and 7 bits here. Now the point I was trying to convey earlier about the positions of RS1 and RS2 can be clearly seen here. So RS1 will always be obtained in these bit locations. RS2 can always be obtained in these bit locations. That's the reason the immediate field has been split here. If a quick example, the add x1, x2, x3 would be represented like this. We have the opcode. RD is 4 zeros followed by 1 because it is x1, followed by function 3, and RS2 is 2, RS1 is 2 and RS2 is 3. Now when we come to subtract, if you look at this machine code closely, the opcode of add and subtract is same, function 3 is same, but there is a difference in function 7. So using these opcode function 3, function 7 together, the hardware can figure out whether it is an add or subtract. Similar thing would happen for the other instructions also. In the I format, we have an example here, ADDI x1, x2 and followed by 100, right? So the, sorry, 1000 is represented here. And if you look at the load instruction, the x1, and we have an offset of 1000 with a base register as x2. That's what is given here. The destination register is x1 here, the base register is x2, to which the immediate value 1000 would be added, right? In the store S type instructions, we have SD x1 1000 x2. So similar, not similar to the load instruction. The opcode is here. The immediate value 1000 is now split into bit positions, right? And followed by function 3. Then RS1 is the base register, which is x2 here, and RS2 is the source operand, which is x1. What we intend here is the value in x1 will be stored in a memory location given by the value in x2 plus the immediate value. So all the fields in this instruction encoding, apart from the immediate field, are treated as unsigned values at the hardware, or we build the hardware to treat them as unsigned values. Now, if we look at these instructions, we see a different interpretation of the same value 1000. Here it is a immediate value, and here it is interpreted as an offset value. Okay, with that I will pause this lecture. All the memory operands were discussed in section 2.3 of the prescribed textbook. So do go through it, and if you have any questions, we can discuss. Thank you.